So what we will learn next is how to actually find the latent factors, or in other words, how to solve our optimization problem. So the thing we want to do is the following, right? We are given the matrix R. We want to represent it as a product of matrices Q and P. The way we want to find matrices Q and P is in such a way that it best predicts the known ratings, right? So what we want to do is we want to solve the following optimization problem, right? We want to find P and Q in such a way that the predicted ratings are as close to true ratings as possible. Now, the idea is, right, we want to minimize the sum of squared errors, which basically means we want to minimize the root mean square error for unknown, unseen data. Because we cannot do this, we will minimize the sum of squared errors on the training data. So I can think of this that I have a function that is depends on matrices P and Q, and I want to find those matrices such that the predicted ratings are as close to the true ones as possible. So now, how do I go and find the minimum of such an error function? Whenever we are given a nice function that we can take derivatives of, the method that immediately comes to mind is called gradient descent, right? So basically the idea is that if we have a simple function, just kind of very abstractly now, that depends on some variables or on a variable x, then the idea is basically we want to compute the derivative of that function, evaluate the derivative of the function at a given point, and then move in the direction the opposite of the derivative or the gradient, right? So the idea is basically if I have some function f that has some given shape, and I want to find the minimum of this function, I would start at some arbitrary random point, let's call it y. I would evaluate the gradient at that point y. It basically means that I would compute what is the slope of that function at that given point, and then I would make a small step in the reverse direction of the slope. And that would give me would get me closer to the minimum. In the next step, I would go reevaluate the gradient. This is how the slope of the line would be, and I would again make a small step in the reverse direction of the gradient, and I would keep doing this until I would get stuck, right? Until kind of I reach the minimum of the function. So this is basically the strategy we'll be using to solve our optimization problem, right? We already have the equation. We can simply take the derivative. This is a simple kind of quadratic equation, so taking derivative is very easy. And we can code up our optimization algorithm in like 10 lines of code. So everything seems to be very straightforward and easy. However, there is one critical component that we will have to add in order for our recommender system to work, right? So we are saying, let's minimize the sum of squared errors on the training data. And here the idea is, right, that kind of we want to pick the number of factors k to be some number and to be enough to capture kind of all the signal. Imagine we pick k of 100. If we do this and observe, for example, measure what is the sum of squared errors on unseen test data, we actually find that as soon as we pick more than 2 factors, our error on the unseen data increases with the number of factors we are picking, right? So let's just say it again. So basically what it seems is that as soon as we are making our model too strong, our model stops working, right? Our sum of squared errors on the unseen test data starts increasing. And in machine learning, this kind of phenomena is called overfitting. And basically, the way what overfitting means is that the model is adapting itself too much to the training data, and the model is basically has too many free parameters. Those free parameters starts to fit noise, and the model has trouble to generalize to the unseen test data. Right? So the problem is that the model is overfitting too much on the training data and doesn't generalize to the unseen data. So it seems like a very hard to solve problem, right? We have a very complex model. We feed this complex model to the data. The model has so many degrees of freedom that it's very easy for it to start kind of fitting the noise. By fitting the noise, the model loses the generalization ability. So the way we go around this problem is by modifying our optimization function. And the particular technique we'll talk about remedy this problem is called regularization. And the idea with regularization is basically that we want our model to have rich structure, right? So kind of to spend lots of modeling power in the areas where we have sufficient data. And then we kind of want our model to be very simple in the areas where we don't have enough data, right? So where kind of the evidence is sufficient for complexity, we want to use lots of modeling power, but in the areas where we only see a few data points, there we want to have the model to be as simple as possible so that we don't start kind of overfitting or fitting the noise. The way we achieve this intuition is that we have our optimization problem now has two components. We have our old part that we already know, the one that I call the error, which is simply how well are we fitting the training data. But then we also have the second part that we call length, okay? And we have this parameter lambda that we call the regularization parameter. And this is some non-negative value that basically trades off between these two competing parts, right? The training error and the length, right? And let's just think about what these two pieces are doing, right? So if we would really just care to minimize the training error, then we could set lambda to 0. The complexity of our model in the right wouldn't really matter, and we would minimize the error. For example, if we don't really care about making good predictions, but we care about our model to be very simple, then we would set lambda to be very high, and all that would basically force is that P and Q would be full of zeros, and this way, again, we would reach the small value of the objective function. Of course, where we want the lambda to be is to be somewhere in between, in some kind of just the sweet spot. So now let me give you some intuition about what is this length part doing to our optimization problem. And the way to think about our objective function is that it has two parts to it, right? There is the error part, and then there is this length part, okay? And think of it the following, right? Think that I have a user. And the way we can think about the following is that for this user, we want to make accurate predictions using the ratings that the user has already made, right? So if this user has made lots and lots and lots of ratings, then there are kind of two parts in this objective function that are trading off each other. So one is that we want to make the error for this user to be small. And on the other hand, we want the factors describing this user to be small. And what does the factors to be small mean? It basically means the distance of the user from the coordinate origin, right? So we are basically now trading off two things. So if we have very little training data for the user, right? If the user rated very few movies, then what will happen is this error part will have only a few movies in the summation. So the value of the error part will be relatively small. Which means that what we will want to do for such a user, we will want to also to make length small, because by making the length small, we'll increase the error, but because the error has only few terms, that won't add too much to the global error. So what will happen is this user will basically start moving more and more towards the coordinate origin. On the other hand, if we would have lots of training data for our user, then we wouldn't really want to move the user towards the coordinate origin, right? We wouldn't want to make its latent factors too short, because the error term would have lots of terms. So we would really want to make accurate predictions for all those terms, and we would tolerate kind of more complex factors for that user, right? So in some sense, what regularization is doing, it's trading off between the predictive performance of the model versus the complexity of the model. Okay? So now, basically, all we have is, we have already decided, right? We have our optimization problem. We want to find matrices P and Q, where we want to minimize both the accuracy of the model, the ability of the model to predict the ratings, plus the simplicity of the model, and our parameter lambda trades off between the simplicity and the predictive performance. One thing to note in this formulation is that kind of we don't really care about the absolute value of the objective function. What we really care about is finding matrices P and Q that minimize that value. And we really want matrices P and Q that actually predict well the unseen ratings. So we are never really kind of want to really find or care about the value of the objective function. We really care about what are the matrices that achieve that value. So now, of course, how do we go and solve this objective function? We can use gradient descent the same way as I demonstrated a few slides ago, right? So we have, even though it looks very complicated, we have a very simple function that we would like to optimize. So the way we do is we apply the gradient descent procedure, where, for example, imagine we initialize matrices P and Q simply using SVD and pretending that missing ratings are equal to 0. That just kind of gives us a good initialization point. And then we perform gradient descent, which means we will repeat these two steps until we obtain convergence, basically until the gradients are very close to 0. And the way this works is, basically we will say, whatever is our estimate of matrix P at time t, we will have small parameter that we call the learning rate times the gradient with respect to the parameters, and then that gives us the value of matrix P at time t plus 1. Now that we have the value of matrix at time t plus 1, we can go to the second step. Here we take the value of matrix Q at time t plus 1, compute the gradient, make the step, and this gives us the matrix Q at time t plus 1. And then we kind of go repeat to the first step. Of course, now how do we compute the gradient of a matrix? That is easy. We just compute the gradient of the equation above. So for example, in our case, I have a summation. So taking a derivative of summation is easy. I don't need to do anything. Then I have this quadratic function. I take the derivative, and then I also have this penalty term. Because I'm taking the derivative, for example, here with respect to Q, P is just a constant, so there is nothing to take for P, and this is what happens for the derivative of Q. And I could compute the derivative in a very simple way, also with respect to P, evaluate my derivative over the training data, and make a small step, and keep doing this until we converge. And this way, we would solve the optimization problem. Now, for example, if we actually go do this on the Netflix challenge and obtain these latent factors, we can ask and set, for example, k equals 2, that we only obtain 2 latent factors, and then map movies into this latent space of the 2 factors. Here is what we see. For example, we see that Wizard of Oz is kind of in the center of this recommender system. And then, for example, here are the kind of bloody movies. And in this part, we get some action movies, and so on and so forth. So you see that basically how the similar movies now get grouped together or in the similar parts of this abstract movie space.